Year 9 probability tree diagrams. Let's consider successive events, i.e. two events which occur one after the other. For example, we flip a fair coin twice. What is the probability of both coins showing tails? What is the probability of each coin showing different results? We can draw a sample space diagram to show all of the possible outcomes. So I can set this up as a grid. This represents what comes up on coin 1, which could be heads or tails. And then here we represent what could come up on coin 2, which could also be heads or tails. And from our sample space diagram, we can see quite clearly heads, heads, tails, heads, heads, tails, and tails, tails. There are 4 possible outcomes which are equally likely to occur. So what is the probability of both coins showing tails? That gives us a probability of 1/4. What is the probability of each coin showing different results? Well, there's the tail heads option and the heads tail option, so that's 2 out of 4, which is a probability of 1/2. We can also draw a probability tree diagram to show all of the possible outcomes. So this is going to be set up like this. The first pair of branches represent what happens on coin 1, and the 2 options are, of course, heads or tails. They go at the end of the branches. The probability of each outcome goes along the branch, so there's a 1/2 probability of getting a head, a 1/2 probability of getting a tail on a fair coin. It's really important that the probabilities, which can be fractions or decimals, go on the branches, and the actual outcomes or events, heads or tails in this case, go at the ends of the branches. We then add in our next pair of branches for what could come up on coin number 2. Now, if coin 1 is a head, then coin 2 could be a head or a tail. Similarly, if coin 1 is a tail, coin 2 could still be a head or a tail. And the probabilities stay the same at 1/2 each time. Now, if I want to calculate a particular probability, I follow the branches of the path I'm looking at. If I follow this branch and this branch, then that is the outcome of getting a head and a head. And I multiply the 2 probabilities. So 1/2 multiplied by 1/2 gives me a probability of 1/4 of getting a head and a head. If I follow this path, that is the outcome where we get a head and then a tail. The probability again is 1/2 multiplied by 1/2, which is 1/4. Looking at the branches underneath, if I follow this path along here, that's the probability of getting a tail first and then a head, which is 1/2 multiplied by 1/2, which gives me a probability of 1/4. Finally, this path here is the path where we end up with a tail and then another tail. So that's a probability of 1/2 multiplied by 1/2, which gives us 1/4. And you can see there, again, the 4 possible outcomes which we could see from the sample space diagram we did previously. So what is the probability of both coins showing a tail? It's this, 1/4. What is the probability of both coins showing different results? So each coin shows a different result. Well, we're looking over here at these 2 possibilities. We have 1/4 and then another 1/4, and we add them together because it's one or the other, and that gives us the answer of 1/2 that we also saw with the sample space diagram. Let's have a look at some examples. Example 1. A bag contains 10 marbles. 7 of these are red and 3 of these are blue. A marble is selected at random and its colour is noted. The marble is then placed back in the bag. This is really important. We then select another marble. So this is called selection with replacement. The marble goes back in the bag, so the bag returns to its former situation. We're going to draw a tree diagram this time to show all possible outcomes, and then we're going to calculate these two probabilities, which we'll calculate on the next page. So here's our tree diagram. So I want a pair of branches which represents marble 1, and marble 1 could be red or it could be blue, and the probability of getting a red marble is 7 out of 10. The probability of getting a blue marble is then 3 out of 10. We then add on the branches for marble 2, and that could be red or blue. And the probabilities are going to be the same as they were before because we put the marble back. So effectively, we still have 10 marbles in the bag and 7 of them are still red and 3 of them are still blue. So here is our tree diagram. I'm going to use that to answer these two questions. So before I look at the questions, I'm going to look at the outcomes of following each of the paths on this tree diagram. This path here, if we follow this first of all, is where we have a red marble and then a red marble. The probability of this happening is 7/10 multiplied by 7/10. Remember, to multiply a pair of fractions, we multiply the numerators, 49, we multiply the denominators, 100. If we follow this path and this path, that means we pulled out a red marble and then a blue marble. The probability of that happening is 7/10 multiplied by 3/10, which comes to 21 over 100. This path here tells us we pulled out a blue marble and then a red marble in that order. So the probability of that happening is 3/10 multiplied by 7/10, which comes to 21 over 100. The last possible path is this one followed by this one, which is where we pull out a blue marble and then another blue marble, which is 3/10 multiplied by 3/10, which gives us 9 over 100. So there are 4 possible outcomes again, but because pulling out a red marble and a blue marble are not equally likely, we end up with different probabilities at the ends of the branches for each of these possible outcomes. So, part 1, the probability that both marbles are the same colour. So the probability that both marbles are the same colour, we either want both of them to be red or both of them to be blue. So it's 49 over 100, add 9 over 100. Remember, when you add fractions together, you need a common denominator, which we have. You then add your numerators together, so we have 58 over 100. Always see if you can simplify, and of course this simplifies down to 29 over 50. Part 2, the probability of choosing a red marble at least once. So at least once means that we can have red red, red blue, and blue red. So that means that's 49 over 100 plus 21 over 100 plus 21 over 100, which comes to a value of 91 over 100. We can also do this calculation in a slightly different way. If you notice, all of the options that we used were these 3 over here, all of which involved at least one red. The only option that we didn't use was this one over here. Now we know that the 4 possible outcomes, red, 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 blue, blue, red, and blue, blue, form the only 4 possible options. So their probabilities must total 1, which means an alternative way of working out the combination of these three probabilities is to do the calculation 1 take away 9 over 100, which comes to 91 over 100. So there's an alternative and slightly quicker way of getting to the same answer. Example 2. A bag contains 10 marbles, 7 of these are red and 3 of these are blue. A marble is selected at random and its colour is noted. This time, the marble is not replaced into the bag. We then select another marble from the bag. And this is called selection without replacement. So we take a marble out of the bag and it's not put back, which means we now only have 9 marbles in the bag when we pick again. Let's look at our tree diagram and set it up carefully. So, marble 1, first of all, and we have two options here. It can be red or it can be blue, and these probabilities are 7 out of 10 and 3 out of 10 again. Now, we then put in the branches for marble 2. And again, the options are red or blue. But we've got to think very carefully about the probabilities. If we follow this branch here, we've pulled out 1 red marble. That means there's only 6 marbles left out of 9 marbles overall because we've taken 1 out. If we follow this path, that means we pulled out a red marble and then we pulled out a blue marble. That means there's 9 marbles in the bag because 1 got taken out, but 3 of them are still blue because we haven't taken out any blues. Similarly, over here, the probability that we would have here has got to be 7 because there's still 7 reds out of 9 because there's only 9 marbles in the bag. And here there are 2 blue marbles left because we took 1 out, and that's out of 9. Also, these probabilities individually have got to add up to 1 as well because it's either red or blue. So that's another way of checking you've got this correct. Here's the tree diagram. Notice I haven't simplified these probabilities here. And that's because if we're not using a calculator, it makes a lot more sense to leave them unsimplified so that we end up with the same denominators once we do the multiplication, and it makes it a lot easier to add them together. So let's work out all of the outcomes and then have a look at the question. So here, if we follow this first path at the top, we're pulling out a red marble and then another red marble, so RR. The probability of that is 7/10 multiplied by 6/9. Again, no simplification. I'm simply going to multiply and write down an answer of 42 over 90, which I'm not going to simplify just yet. Do it at the end. It's much easier. Over here, we have a red marble and then a blue marble. So that is RB, which is 7/10 multiplied by 3/9, which gives us 21 over 90. This path, blue followed by red, which is 3/10 multiplied by 7/9, which is 21 over 90. Notice that these are the same, regardless of which order we pick them in. And then lastly, we have this path here, which is the path of blue, which is 3/10 multiplied by 2/9 as a probability, which is 6 over 90. So let's work out the answers. First of all, find the probability that both marbles are the same colour again. So the same colour refers to red and blue. So this time we add them together again, 42 over 90 plus 6 over 90. You'll be glad at this moment, if you're not working with a calculator, that you didn't simplify the fractions. They would then have different denominators and you'd have to spend more time giving them the same denominator. Here we can just add them easily to get 48 over 90, which we can then simplify down to 8 over 15. Part 2. The the probability of choosing a red marble at least once. So again, we'll look at the two possible ways of doing this. So we could have two reds, we could have a red and a blue, or we could have a blue and a red. So my probabilities are 42 over 90 plus 21 over 90 plus 21 over 90, which gives me a value of 84 over 90, which we can simplify down 14 over 15. Alternatively, we can work out one takeaway, the only option that we aren't allowed, which is this one, which has no reds at all. So 1 takeaway 6/90ths, which again, if you want to, you can think of it as 90/90ths take away 6/90ths, and that again gives you 84/90ths, which simplifies down as before. Example 3. The probability that it rains on a particular day is 0.6. If it rains, the probability that I am late to school is 0.8. If it does not rain, the probability that I am late is 0.5. Now, this part's really interesting because the probabilities of being late depend on whether or not it rains, and that's an example of what we call conditional probability. We're going to draw a tree diagram to illustrate this information. So here we have, on our first level of branches, whether or not it rains. So I can write rain, and if I want to, I can write not rain, or you might like to write R dash, which also means it's not raining. It's the complement of raining, which is to not rain. Now, the probabilities here are 0.6 and 0.4 as decimals. You do not have to convert those to fractions. Now, the next events that we look at are whether or not we're late. So we can have late, not late, late, and not late. Now, let's read this information again. If it rains, the probability that I'm late to school is 0.8. So that 0.8 depends on it having rained. This number here is then 0.2, so the two branches together have a total probability of 1. If it does not rain, the probability that I'm late is 0.5, which means this probability here is 0.5 as well. And we have a complete tree diagram. So here's our tree diagram again. Let's work out some probabilities. So if we follow this path here, we're looking at it raining and being late. So that's 0.6 multiplied by 0.8, which is 0.48. Here and here, these branches, that's raining and not being late. So that gives us 0.6 multiplied by 0.2, which is 0.12. No rain, but being late, 0.4 multiplied by 0.5, which gives us 0.20. And then no rain and not late, which is 0.4 multiplied by 0.5, which again is still 0.2. And you can see that these numbers here all add up together to make 1. So let's find the probability that it rains and I am not late to school. So we want it to rain and not be late. So we're looking at the probability of 0.12. The probability that I am late to school. So we need to find all the branches that end up with being late to school and highlight those. So let's find them. So the probability of being late to school, well, it could rain and you could be late. So that's this one. And it could not rain and you could still be late. So that's this one as well. So we need to make sure we include these probabilities in our answer. So we want to do 0.48 multiplied by 0.20, which comes to a total of 0.68.